let's say that we were looking at the graph of 1 over x squared. So I'm going to show you what I'm talking about. All right, here's the graph of 1 over x squared. It's got some other stuff on there too. But there's the graph of 1 over x squared. And say we wanted to know the area under the curve, maybe from 1 here to infinity. You know, summing up all this down here too. Now this line 1 over x squared, it never touches the x-axis. It just gets closer and closer forever and ever. So, you know, you would think that you could just say, okay, from 1 to infinity of 1 over x squared dx. And you actually can. But in math, a lot of times the notation is important. Okay? And since infinity is actually not a number, the way that we prefer to write something like this is let infinity be some variable. And usually, you know, we have the integral from a to b. Usually, if it's a top boundary, we let it be b. So what if I wrote this integral as the limit as b approaches infinity, the integral from 1 to b, 1 over x squared dx. And so then I could integrate. So how do you integrate x to the second? Well, think about that like it's x to the negative 2, right? So you add 1 to the power and you divide by the new power and you get what? Negative 1 over x. And we're going to evaluate that from 1 to b. And remember, we're letting b approach infinity. But I can just work this out and plug in a b. So this is negative 1. This is, I'm going to keep my limit notation. This is the limit as b approaches infinity of negative 1 over b minus, right, because I have to subtract and then plug that in, negative 1 over 1. Now I can let b approach infinity here. And so that would be negative 1 divided by infinity. So that's 0. And then I have minus negative 1. So plus 1, which equals 1. So the actual area under the curve from 1 to infinity of 1 over x squared is equal to 1 square unit. Now, notation is important in math. So that's why we write the limit notation in front. Sometimes when we work out these integrals, we come to something that'll be in an indeterminate form, but we can apply L'Hopital's rule, the stuff we learned in the last section. And so that's what we do if we want to have an upper limit of infinity. If we want to have a lower limit of negative infinity, like this, say we want to go from negative infinity to 0. Well, usually this bottom here, we would let that be a. So instead of writing your integral like that, you may want to say the integral from a to 0, but then to say the limit as a approaches negative infinity. Okay? And then work out the integral, you know, at the very end, after you have everything in terms of a and 0, then you can say, okay, well, a is negative infinity. What does that do? Okay? And you can also work integrals from negative infinity to infinity. But if you do that, a lot of times you want to split it up, find some convenient point where you can split the integrals up, and instead of going from negative infinity to infinity, of some function, maybe go from negative infinity to some convenient value c, plus the integral from c to infinity. You know, because sometimes if you don't, your integrals just won't come out right. So you need to make sure you split those up. And c can be any value. The most convenient value is usually 0, but it doesn't have to be 0. In any case, if you get an answer out for one of these integrals, these are called improper integrals, by the way. These are improper integrals. But if you get an answer out for these improper integrals, then it's said that the integral converges. Answers mean converge. So if you can get an answer out, the integral converges. So that's if the integral exists. If it doesn't exist, if you get infinity or negative infinity as your answer, we say the integral diverges. Okay.